Yeah, welcome all. I am myself Balakrishnan from CSE department. Today we are going to discuss about the operating systems. In the operating system, particularly deadlocks. So it is one of the important topic in operating system. So first we can see what are the contents we are going to see here. Contents here, just a brief about what is deadlock, definition of deadlock, just to have the idea about that. Next, deadlock, how it occurs, the reasons for the occurrence of the deadlock, then how to prevent, some strategies will be there, what are the prevention strategies. Next one is whenever we want to avoid that, how the resolution techniques can be used, and some question sample also we are going to see here. So let us move to the topic. Okay, so what is deadlock? So everybody knows that also, but whenever you are studying in the operating system also, you might have studied. So just if you have a brief idea, then it will be further to follow, it will be easy. So a deadlock is a situation in which computer programs sharing the same resource, okay, so are effectively preventing each other from accessing the resource. So what happens is, whenever a shared is there, it will be many resources are there, but whenever the processes are more than the resources, so whenever they want to share, what happens here? So the access is resulting in both programs ceasing to function. So whatever the program, so that it won't be the program, whatever the process want to want some resource, whenever they are searching for the same resource, they can't do that. So it will be, the program will be ceasing to function. So we can't do the operating system functions cannot be done properly. So that is the thing. Next, reason for deadlock. So what will be the reason for deadlock? Let us see that also. Deadlock, some common causes will be there. What arise due to various reasons, such as what we can take is poor resource management. The resource, whatever the resources for the operating systems, whenever it is not managed properly, that also will be the reason. Another one is incorrect synchronization. The process won't be synchronized properly, so that the whatever the process which is searching for some resources, it won't be synchronized properly. Some kind of incorrect synchronization will be there. So that also one of the reason, or insufficient system resources. Whenever the system resources are insufficient, that also may be the reason. But some common causes are there. Whenever see here, the limited resources, when the system does not have the resources to satisfy the requirements. So that is also one of the reason. Another is incorrect resource allocation. So the resources should be properly allocated to the whatever the process which in need of the resource. So that also one of the reason. If the resources are not allocated properly, so with the process holding resources, we are waiting for others. Okay, some kind of process will be holding the resources, so that whenever it's not needed also, it will be holding. That allocation is very much important here. So deadlocks can rise there also. Next one is inadequate synchronization. Improper synchronization of the process also can lead to deadlock situation. So whenever in a multi-threaded application, some kind of multi-threaded applications are there, whenever we are using an operating system, whenever we are doing many type of activities, it will be doing the multi-threaded applications. So there also some problem may come. So here next one is how we can prevent that. One important concept is resource allocation strategy. What type of strategy can be used for allocating the resource? So this is a graphical representation, helps to identify which all you know that, and avoid the deadlocks by tracking the allocation and request according to the whatever the process request. Whenever the process requests some resource, there also we can. Next, second one is the Banger's algorithm. This algorithm ensures that the system remains in a safe state. So what is the Banger's algorithm? You know that the Banger's algorithm, whenever whenever they want to give a loan in the bank, what happens is whenever they having the sufficient fund only, they will will be availing the loan to customer. So they will be in a safe state to allocate the loan. So the same principles used here. The allocation ensures that the system remains in a safe state by considering the available resource and maximum demands of process before allocating the resource. So what is the maximum allocation of resources are there? Accordingly, the banker's algorithm will distribute the resources to whatever the process requiring the resources. Next one is timeouts. Implementing timeouts for resources request can be prevent deadlocks. That also one of the reason by releasing the resources held by a process. So whenever the process, whenever it uses the resource, it should be released on time. So that is the timeout. What is the timeout for releasing the process? That also is used. If it fails to acquire the necessary resources within a specified time, whenever the process is given a resource, it must use it at a proper time. Whenever it taking more time, it must be some timeout reason must be there, so that they can come out of that and the resource is released there. Next, process resolution techniques, process termination. If a deadlock is detected, one or more process involved can be terminated. So that is known as process terminated. If it is detected deadlock, so one kind of whatever the resources, some kind of resources can be terminated from that, so that we can avoid the deadlock also. So however, that whenever we are using the resources, what happens is we should be very much careful here is it creates the data corruption. So that's we have to avoid the data corruption, or loss of data may happen whenever you are not using it wisely, the process termination. Next one is resource preemption. Resources can be preempted from one process and allocated to another to break the deadlock. So one process that can be for using it, whenever we can preempt, so that the other process can use the resource. That also. So here also we should be careful to avoid causing more problems. So whenever that process may be held or another process won't be working properly, that kind of whatever after that what kind of problems, that also we have to face that properly. So next one is that if a process cannot request 3 printers, if the system has only 2, a process may utilize the resource in the following sequence. So some sequence of things are there. A process, suppose a process requires 3 printers. A process wants 3 printers of that. So how to do that? So 3 things are there, have to be followed. That request, use and release. What is request? The process requests the resource. It must request for the resource. If the request cannot be granted immediately, what happens? Requesting process must wait until it can get the resource. That is one is request. We have to make the request of the resource. That is the first one. Next, the use. What is use is the process can operation on the resource. If the resource is a printer, the process can print on the printer. So suppose the operating system want to print something that according to the user uses the printer. So that can be done. Next one is release. The process release the resource. After using the resource, it must be properly released by the process has to release the resource. So necessary condition for a deadlock, whenever we are speaking about mutual exclusion, first one is mutual exclusion. Only one process at a time can use the resource. That is the concept of the mutual exclusion. Next, hold and wait. What is that? A process must be holding at least one resource and waiting to acquire additional resources. Hold. It should be, suppose if you want more resource, it has to hold for some time and wait for that and get the resource. That are currently being held by, because that whatever the resource they want may be used by some other process or something like that. So that is the thing. Next, third is preemption. Resources cannot be preempted. A resource can be released only voluntarily by the process, because the process may be using the resource, so they can't be at least the process, whatever the process using the resource must voluntarily release that, then only. So no more preemption is there. So whenever that also will be leading to the whenever we need preemption, but if no preemption is there, that also lead to the deadlock. Next one is circular wait. Suppose a set of process, n process are there. P0, P1 up to Pn is there means, so of the waiting process exists, so such that P1 is waiting for the resolution held by P1. Similarly, P1 is waiting for the resources held by P2. Like that it goes. Finally, what happens is Pn will be waiting for the resources for a resource held by Pn. Pn n minus 1. Similarly, that and Pn is waiting for the resources held by Po. So, the cyclic wait will be going there. That also it may be the reason for that. So deadlock can be prevented by certain concept, mutual exclusions, not required for shareable resources, but hold for not shareable resources. That also one of the thing for the deadlock prevention. Another one is hold and wait. Must guarantee that whenever a process requires, it does not hold any other process. It has to. This is one of the important concept here, that whatever the required process and be allocated all its resources before it begins execution, allow the process to request resources only when the process has none. So that is another concept. Okay, whenever low resource utilization, starvation possible. Whenever the resources are not used properly, what happens? Starvation will be happening in the system, whatever the operating system. So this is the hold and wait. Next one is no preemption. That also we have seen, that if a process that is holding some resources request another resource, that cannot be done immediately. So what happens? The preempted resources are added to the list of the resources for which the process is waiting. Whenever it is with that, it will be added to that. So that is the thing. By preemption, it will be added. Process will be restarted only with the regain its old resources. That whenever what it has requested resources, that also can happen. So as the new one that is requested, because new type of processes will be added and it will be requesting for some resources. That also will happen here. Circular wait impose a total ordering of the all resource types and require that each process requires for resources in a increasing order of enumeration. Whatever the thing is, circular wait also we have seen here. Next, deadlock avoidance, how it can be avoided, that whatever the thing, simplest and model requires that each process declare the maximum number of resources. So how we can avoid the deadlock? Deadlock, whenever whatever the, suppose we give more resources to that, then there won't be any resource. Everybody will be using that whatever the resource they possible. The deadlock avoidance algorithm dynamically examines the resource allocation. So resource allocation state is defined by the number of available and the allocated resource. Some kind of problems also we are going to see in that, and the maximum demands of the process can be done here. Safe state, this is also one of the things. When the process requires an available resource, the system must decide if immediate allocation leaves the system. Whatever the allocation, whenever it is used the resource, that whatever the resource must leave the system in a safe state. That is the thing. So the system is in a state, if there is a sequence, so P1, P2, P1, if we say all the process in the system is such that for each PI, the resources that PI can still request can be satisfied. So any other resource, whenever any process is demanding for some request also can be satisfied by currently. That is known as the safe state of a system. Okay. So plus resources held by all the whatever the things that process may be there, with see here that with j less than 1, that it must be less than 1. So that is, if PI resource needs are not immediately available, then PI can wait until all PJ has finished. That is the thing. So when PJ is finished, PI can obtain needed resources, execute, return allocated resources and terminate. So that is another thing. So whenever PI terminates, PI plus 1 can obtain its needed resources, and so if a system in a safe state, no deadlocks will happen. So if a system is in unsafe state, state possibility of deadlock. So that is the importance of the safe state. Whenever it is in safe state, what happens? There won't be any deadlock. If it is not in if it is in an unsafe state, there will be more chances of the deadlock happens. So avoidance ensure that the system will never enter an unsafe state. So that is the importance of deadlock avoidance. What happens? The system will never move to the unsafe state. So avoidance algorithm, since in instance of a resource type, use a resource allocation graph. That is one of the important concepts used in operating system. Multiple instances of a resource type. Another thing is the Banger's algorithm can be used. So let us see some of the whatever the important, some kind of questions we can see that, and then how we can explain how to explain the question, and then how to get the answer for that. So here the first question is, what about the thing is, computer has 6 state drives with n processes competing them. Okay, so what each process may need 2 drives. What is the maximum value of n for the system to be deadlock free? So here whenever he see here that read the question carefully, the computer has 6 state drives with n process competing for them. So what each process may need 2 drives. So what will be the answer? The option A is 6, option B is 5, option B is 4, option C is 4, and option D is 3. So how to justify the answer? The answer is B. How it comes here? So given tape drive is equal to 6. Okay, so the given, and each process may need 2 drive. So when we give 1 drive to one process, then the total process will be 6. But in this case, there will definitely deadlock occur, because why it occurs is every process contains 1 drive and waiting for another drive, which is held by other process. So therefore, when we reduce the process, reduce one process, then system to be deadlock free. So here what it should be, a maximum value of n is equal to 6 minus 1. So whenever this kind of 5 means what, it will be deadlock free. So that is the thing here. So option C is here, the option B is correct answer. The 5. Next. Question 2. The solution to the dining philosopher problem which avoids deadlock. So whenever carefully we read the dining philosopher problem, whenever it is one of the important concepts used in operating system, so we can see from that also. So what it tells is, ensure that all philosophers pick up the left fork before the right fork. Ensure that all philosophers pick up the right fork before the left fork. So see the difference in that. Next, C. Ensure that one particular philosopher picks up the left fork before the right fork, and that all the other philosophers pick up the right fork before the left fork. Option D is none of the above. So let us see about what is the difference here. Left fork before the right fork before the left fork. Then last one is none of the above. So here what the dining philosophers say, it ensure that one particular philosopher picks up the left fork before the right fork, and all other philosophers pick up the right fork, okay, before the left fork. That is the thing. When one philosopher is picking up the left fork before the right fork, what others will be doing, all other philosophers will be picking up the right fork. So what right fork means, that whatever they are having in the right side of that wherever they are sitting. So that one. So which avoids the deadlock condition. So here what happens, the option C is here the answer for that. So ensure that one particular philosopher picks up the left fork before the right fork, and that all the other philosophers pick up the right fork before. So this is the answer for this one. Next, question number 3. So what what they have told here is, a system shares 9 tape drives The current allocation and the maximum requirement of tape drives for 4 processes are shown. Here 4 processes are there, P1, P2, P3, P4, and what is the maximum need for them? Here the maximum need for P1 is 9, P2 is 6, P3 is 5 and P4 is 10. Next, what is allocated? Current allocation of the whatever the resources done here is 3 for P1, 3 for 1 for P2, 3 for P3 and 0 for P4. Let us see about that one. What is the question here is, which of the following best describes the current state of the system? Whenever the system is described like this, what will be the thing? Whether option A, safe and deadlock, whether option B, safe and not deadlocked, option C, not safe and deadlocked, option D, not safe and not deadlocked. So let us see from here that from the explanation there are 9 tapes and allocated is whatever the allocated is 3130. So what is that is totally 7. So remaining available tape is what is that 9 minus 7 is equal to 2. So that is the thing available. So let the remaining need for here we need 9. So the maximum remaining need here is 6 for the process P1. For the process P2, here because 1 is only allotted, current allocation it needs the 6, so it needs 5. What about the process P3? It's the need for 3, only 3 allocated, so remaining need is 2. Process P4, maximum need is 10, nothing is allotted, only 0 is allocated, so it needs all the 10 resources. Okay, so let us see about that one. So now we can satisfy, so now we can satisfy one process P3 for which only 2 tapes then currently available will be total 5, whatever the shown there. Similarly, we can satisfy only process P2 which requires only 5 tapes, then current available will be totally 6. Okay, then we can satisfy only process P1 which requires only 6 tapes, then current available will be total 9. So, but we cannot satisfy remaining need of the process P4 because it requires 10 tapes here and remaining need 9. So, option C is correct. So, what is the answer here? Let us see from here. So, option C is not safe. It is not safe because what? It requires not properly allocated for that one, and deadlock certainly happens here. So this is the thing. So deadlock will be happening here whenever because none of the resources can be allotted for the process P4. Next. Consider a system with 3 processes that share 4 instances of the same resource type. So, same resource type, 4 instances have been shared by 3 processes. So, each process can request a maximum of k instance, whatever the thing. So, what will be the resource instances can be requested and release only one at a time. That is the condition here. So, what will be the largest value that will always avoid deadlock? So, by keeping what value of k so that we can avoid the deadlock. So coming to that, let us see about that one. So here explanation, the number of process is P is equal to 3, number of process resources is 4. So what is the deadlock free condition here mentioned? The resources is equal to, it should be greater than or equal to the process, number of process into n minus 1 plus 1. So where R is the number of resources and P is the number of process and N is the maximum need for the resource, so whatever the things. So whenever we apply that, whatever the given values, what we get is 4 is greater than or equal to n minus 1 plus 1. So is equal to 3 is equal to greater than or equal to 3 into n minus 1. So greater than or equal to n minus 1 into n less than or equal to 2. So what we can keep is here the deadlock to avoid the largest value of k can be kept. So the what value we can keep is 2. So option 2 is correct here. See here. Option 2 is the largest value will avoid the deadlock is option 2. Next, what problem is solved by Dijkstra's-Banger's algorithm? So that whenever we see the definition of the Dijkstra's-Banger's algorithm itself, we can see that it is catch coherence or mutual exclusion or deadlock recovery or deadlock avoidance. So that we can, whenever we read the Banger's algorithm, we can understand that the option D is from the option, what is that is deadlock avoidance. What happens? The Banger's algorithm gives the whenever we apply the Banger's algorithm, deadlock avoidance can be done. Next, with single resource deadlock occurs if there are more than option A is if there are more than two processes competing for the resources. So if there are only two processes competing for the resource, if there is a single process competing for the resource or none of these. So what we can with the single resource deadlock occurs whenever a single resource are there. So what will be the situation there deadlock occurs? So whenever see that options carefully, if there are more than two processes competing for the resources, if there are only two processes competing for the resources, if there is a single process competing for the resources. So here let us see about that. What will be the explanation here? The answer is D, option D. There are four conditions required. We know from that we already know that what are the four conditions required for a deadlock to occur: mutual exclusion, no preemption, hold and wait, and circular wait. But when there is only resources, the conditions for hold and wait and circular wait gets eliminated. Circular wait when it comes, when whatever the to hold and wait and circular wait when it comes. So whenever many resources are there, then only it will be waiting for that, or it will be in a what circular wait it will be waiting. But here what only when there is, so that is eliminated. That option get eliminated with the assumption of no process can use the resource for infinite amount of time. Whenever a process will finish, another process can get the resource. So that is the, so deadlock can't occur. Deadlock can't occur. So option D is the correct here. So which of the following is not a necessary condition for deadlock whenever we are keeping the question like this? So what we get is the option A is mutual exclusion, re-entrancy, hold and wait, no preemption. Let us see what is the option for this one. So here one important concept here explained is re-entrancy. There are four necessary conditions for, we already know that, there are four necessary conditions for deadlock to occur: mutual exclusion, no preemption, hold and wait, and circular wait. So whenever why they are telling is option B is re-entrancy is a programming concept where a function or subroutine can be interrupted and they resume it finish the executing. So this means that the function B can be called again before it completes its previous execution. So any function can be called. So what here re-entrancy is a programming concept where a function subroutine can be interrupted and then resumed before it ends. This means that the function can be called again before it completes the previous execution. So whenever it is not completed the previous execution, at the same time it is through the subroutine it is called. So that's why that option here, the option B, re-entrancy is the correct answer. Which are the following not a necessary condition for deadlock? So that also, so that deadlock here, mutual exclusion must be there, hold and wait must be there, and no preemption. So you must know about the what is re-entrancy, that properly. So next one is question 8. What is that? A total of 9 units of a resource type available and given the safe state below here. Whatever the, which of the following sequence will be a safe state? So here 4 processes are there. What are the things used here? What are the resources used? 2, 1, 2, 1. So here the maximum whatever the allocated is 7, 6, 5 and 4 for things in the according to that. So here what are the options? Either it may be P4, P1, P3, P2, whatever the allocation will be. P4, P2, P1, P3. Option C is P4, P2, P3, P1. Option D is P3, P1, P2 and P4. So here whenever let us see the explanation by applying the Banger's algorithm. Okay, by applying the Banger's algorithm, what is the need for the resources here for the process. So here already, so maximum 5, 3 that they have given. So how it comes here is option currently available, sorry. So what is the thing is, read the question carefully, that used is here. So whatever the used, so how much is required? 5. Here 5 is required. Here 3 is required. Here 3 is required. That only they have shown here. That only they are shown here in the maximum required. So currently available resources, available minus the allocated resources is equal to 9 minus 3 is equal to 6. So if the process request of the P1 is granted first, then it would release a maximum number of 4 resources after its execution. And if P1 or P2 are allocated next, then the request cannot be fulfilled as both of them require 5 resources according to the chart, that matrix we have shown. So that eliminates option A, B and C. Option D is the correct. So according to this, the option D is correct. P3 first allocated, P1 next P2 and P4. Then only without deadlock we can allocate the resources. Question 9. When a process is rolled back as a result of deadlock, the difficulty which arises is starvation. Either it's starvation or it is system throughput or it's low device utilization or cycle stealing. What are the process cycle stealing? So let us see about that. Here they are given the answer as answer A. What is that? When a process is rolled back, whenever the process is rolled back as a result of deadlock, whenever a result deadlock happens, we need to roll back the resource. So whenever we do that, what happens? The difficulty which arises is starvation will arise. The resource won't be allocated. What happens? Roll back the process, then there may be possibility that again deadlock occur. So there may be again deadlock may occur. So continuously if it occurs, certainly some kind of starvation will be there. After that again process will wait for indefinite amount of time, that will go to starvation, leads to starvation. That is that. So on the other hand, low device utilization and cycle stealing is not a related concept to the rollback. Whenever we have read this concept, low device utilization and cycle stealing, so this is not related to the rollback of the process as the result of the deadlock. So option A, starvation is the correct answer. Okay, starvation is the correct answer here. Next, question 10. In which of the following 4 necessary conditions for deadlock process claim exclusive control of the resources they require? So, which here, whatever the conditions for the things, deadlock, no preemption, or option B, mutual exclusion, or option C, circular wait, or option D, hold and wait. So, let us see that. So, explanation what here you given is answer is B. So what mutual exclusion is a condition when more than one resource are not shareable. When mutual exclusion come, whenever the more than one resource not shareable, whenever it happens like that. So only one process can use at a time. So that is the thing. So here what process claim exclusive control of the resource they require. So option B is the correct answer. 11th question, consider system having m resources of the same type. These resources are shared by 3 processes A, B and C which have peak demands of 3, 4, 6 respectively. So these things, whenever in the peak of working, they need that kind of things. The minimum value of m that ensure deadlock will never occur is 11, 12, 13 and 14. Let us see the explanation and the answer. Okay, here they have given the answer as answer is A. A is selected is option A is selected is explanation. So what? Let the resources needed by P1 is equal to R1 is equal to 3. First one we keep that. Then number of resources needed by P2 is equal to R2 is equal to 4 and so on it goes. So here when the minimum resource required to ensure the deadlock will never occur is R1 minus 1 plus R2 minus 1 plus R3 minus 1 plus 1, whatever the thing. So here what happens is 3, the value, whenever we allocate the value, R1 is equal to 3, so what, 3 minus 1, R2, P2 is equal to R2 is equal to 4, so 4 minus 1. Next one is R3 is equal to 6, according to that, 6 minus 1 plus 1 is totally 11. So option A is correct. So according to whenever the peak demands 3, 4 fixed, especially whenever we keep, the value of the network won't occur is whenever we keep like that. Okay. But also the answer they have given us D. So let us explain that about that whatever the answer for for D. So the value of n for which the deadlock can't occur is n into the, according to the formula, n into k minus 1 plus 1. So whenever we apply that, the minimum number of resources required is equal to m minus 1 plus 4 minus 1 plus 6 minus 1 plus 1, so 11. So that is the D is the correct answer. System contains, question number 13, the system contains 3 programs and each requires 3 tape units for its operation. The minimum number of tape units which the system must have such that deadlocks never arise is, what are the, here they have given 4 options are there, 6, 7, 8 and 9. Okay, the system contains 3 programs and each routine, if 6 resources are there, then it may be possible that all processes have 2 resources and waiting for 1 more resource. Therefore, all of them will have to wait indefinitely. So that is the thing. If 7 resources are there, then at least one must have 3 resources. So deadlock can never occur. So that's why we are giving us question number 14. Let us see what is the question read. That 4 policies they have explained here. Process should acquire all their resources at the beginning of the execution. If any resource is not available, all the resources acquired, whatever the acquired can be released. So next one is the resources are numbered uniquely and process are allowed to request for the resources only in increasing resource numbers. According to the, whenever the resources are increasing in order, it can be allotted like that. The resources are numbered uniquely and process are allowed to request for resources only in decreasing resource numbers. That is another policy. The 4th policy what they have told is the resources are numbered uniquely. A process allowed to request only for a resource with resource number larger than its currently held resources. That is the 4 policies. Let us look at the question here. Okay, which of the above policies can be used for preventing deadlock? Any one of 1 and 3 but not 2 or 4, any one of 1, 3 and 4 but not 2, any one of 2 and 3 but not 1 or 4, any one of 1, 2, 3 and 4. Let us see the answer for this one. See here that they have given the answer is D, the option D. Explain whenever, if first is followed, then hold and wait will never happen. So what? Continuously it will be 2, 3 and 4 are similar. If any of these followed, cycle wait will not be possible. Let us see. So one process should acquire all the resources at the beginning. If any resource is available, all the requests occurred so far release. So that is the thing. So whenever we follow that, others are followed properly. So that is any one of 1, 2, 3 and 4. So that is cyclic wait will not be possible because it is not in a cyclic, whatever the resources required for the process. Next we move on to question 15. A counting semaphore was initialized to 10. Then 6P wait operations and 4V signal operations were completed on the semaphore. So the resulting, the option they are given for the semaphore, whatever the value, A is 0, B is 8, C is 10 and D is 12. So let us see the answer for that. The answer is B. So how they are explaining the thing is for the justifying the answer B. Initially we have semaphore value 10. Now we have to perform 6P operation, isn't it? So when we perform 1p operation, it decreases the semaphore value to 1. So that normally occurs, that is the semaphore happens. Okay. So after performing 6p operations, we get semaphore values is equal to 10 minus 6. So whatever the 6 value have been taken. So it will be, remaining will be 4. And now we have to perform the 4v operations, means when we perform 1v operation, it increases the semaphore value to 1. So that is the value. So after performing the 4v operations, we get semaphore values is equal to 4 plus 4 is equal to 8. So option B is correct here. Option B is correct. The resulting value of the semaphore will be this thing. So question 15, the last question for this one. A critical section is the program segment, so which should run in a certain specified amount of time. Critical section, whatever that. Which avoids, option B is which avoids deadlock. Option C is which shared resources are accessed. Option D, which must be enclosed by a pair of semaphore operations P and V. Let us see the what will be the answer for this. So answer C. How we get the answer C is critical section. So what? According to the definition of the critical section, the part of the program where shared resources are accessed by process. So whenever the critical. So it also contain. So what is the, according to the definition of the critical section 1? It contains the shared variable or shared data, and the rest portion of the program is called non-critical section. Because critical section means what? That some kind of shared data or variable will be there. So that. So what? Here the option C is correct. Okay, thank you.